Good evening, everybody. So, we are talking about the different types of magnetic properties of the metal complexes, and today we will see about the magnetic measurements, where we can see how experimentally we can determine the different magnetic moments of these metal complexes. And what we have seen in our previous classes, that if you have two centers and these two paramagnetic centers, it can be in any solid sample or it can be any biological sample also, such as that of in hemocyanin, where this particular center having one unpaired electron and the second is also having second unpaired electron, and this can be compared with some other species like that of our simple copper complex, which is mononuclear. So, if we have a mononuclear complex and this is obviously a dinuclear one, and these two systems we can simply compare by knowing the corresponding magnetic moment values. If this is simply the corresponding spin only value, we can have one theoretically predicted value and another one is the experimentally determined quantity. Similarly, here also we can have the theoretically predicted one and the experimentally determined the corresponding one. So, in this today's class, when we go for these typical measurements, if initially we can consider that theoretically we can have some idea about the total magnetic moment, it can be in both these two cases the spin only, that means the spin contribution we are only considering, then we can have some magnitude of these depending upon the number of unpaired electrons. So, what are the unpaired electrons present in these two systems, that can immediately tells us that what would be the corresponding magnetic moment. So, based on these values we basically get the corresponding theoretically predicted magnetic moment values. Then we will see how the different techniques, the physical techniques we can use to measure these magnetic moments, starting from the simple mononuclear or dinuclear or tetranuclear complexes of any coordination compound containing the transition metal ions or the lanthanides or the actinides, and we can compare these values with that of the corresponding values what we get from the theoretical calculations. So, these theoretical calculations are very useful considering the number of unpaired electrons in these systems. So, these measurements basically gives us some very good idea that what are the different types of interactions we can have for the overall magnetic moment of the system. So, this we have seen already, that when we have these number of unpaired electrons in the different metal ions and these metal ions are bound to the ligand system, it can be to the biogenic ligand system like that of porphyrin or any other protein derived ligand system also, and then we just simply can focus our attention on the spin magnetic moment. So, the spin magnetic moment basically giving us the corresponding spin only values, which are ranging from 1.7 to 5.3 for a system having one unpaired electron to 5 unpaired electrons. So, side by side when we will see that these two values in this, the values what we are getting in this column are the theoretically predicted values based on the number of unpaired electrons and their corresponding spin values, total spin values, and on the right hand side what we get experimental one. So, the theoretically predicted one and the experimentally determined quantities always we should compare, and in some cases we will see afterwards that there is some deviation from the theoretically predicted calculated magnetic moment values with that of our experimentally determined values, then only we can assume that there is some mechanism operating which can either increase the magnetic moment or decrease the magnetic moment what we can predict from these theoretical calculations. So, in some cases we can see that the magnetic moment values are in excess of what we have calculated from the spin only values. Then something else is contributing towards the total magnetic moment, and we will find that if we just consider the orbital magnetic moment values together with the spin values, then only we can justify some of these excess amount of magnetic moments, particularly when we are considering a magnetically dilute system where the system has the separated metal ion centers containing unpaired electrons which are isolated by the ligand environments. So, they are not close enough to each other and they are not interacting to each other to give us a magnetically concentrated system, and we can have the other two types of interactions such as ferromagnetic as well as anti-ferromagnetic interactions for these systems. So, if we have these similar unpaired electrons for these systems, and when we have 5 unpaired electrons on a ferric ion giving rise to a magnetic moment value of 5.92, we simply say that the corresponding crystal field is not changing the presence of the unpaired electrons which are 5 in number. That means we are considering a system which is simply the high spin system. That means the crystal field is not strong enough to go for any spin pairing. So, the similar calculations considering the formula what we are using depending on the n values for the mu in units of mu b, we can do for the other low spin complexes at the same time. So, we can have two values for either the high spin complexes or the low spin complexes, and we can find out that in some cases we can have the magnetic moment less, or in some other cases we can have a magnetic moment greater than what we can theoretically predict. So, if we have a simple paramagnetic system and we will take the help of the temperature dependence of the susceptibility term or the magnetic moment term, and if we can go for a variable temperature measurement for these values. So, whatever magnetic measurements we can have, we can go for a variable temperature measurement where we can see that how the corresponding chi m values are changing with that of the change in the temperature, because some of these magnetic interactions are seen at a very low temperature. So, in the low temperature domain or in the low temperature regime, we see the corresponding interactions. So, at this particular temperature, what we are talking in our last class, that we can have the corresponding multiplet width, and if we go down with this temperature, we are basically manipulating the corresponding thermal energy packet, that means the corresponding kT value that we are changing, which is at 300 Kelvin, that means the room temperature is around 205 to 210 centimeter inverse. So, as we go down to either to a liquid helium temperature or liquid nitrogen temperature, our K2 values are changing, and we have a different types of populations for these different magnetic orbitals with that of the available unpaired electrons on the complexes, whether the complex is a mononuclear one or a dinuclear or a higher nuclearity So, when we see that a simple paramagnetic species, it can be a biological species, it can be a catalyst, it can be any solid state material, it basically gives us some idea that when we go the change in temperature, that means the when we go for increase in temperature, the corresponding susceptibility, that means the gram susceptibility values as well as the molar susceptibility values are decreasing. But this decrease is very much monotonous, and we can have some relationship with that of our chi m values with that of our temperature that we basically get from the Curie equation, and as a result we can have also the corresponding constant for this type of plot of susceptibility versus temperature. But if we find in some other case that an interaction is taking place between two or more centers, and the system we can consider as an antiferromagnetic system, that means they are coupled antiferromagnetically. That we have seen in case of the simple metal salt. What we can have in any chemistry laboratory is the corresponding copper acetate salt, where 4 copper acetates are there along with 2 water molecules which are binding towards this copper center in square pyramidal environment. So, the square base is forming from these acetate bridges. So, these are the corresponding acetate bridges, and these are the 2 water molecules. So, we have typically one unpaired electron on this copper center and the second unpaired electron on the other center. So, in this particular situation, what we see that the true energy levels we can have due to the corresponding exchange interaction between these 2 unpaired electrons, which we consider as the corresponding super exchange behavior for these 2 centers, and one unpaired electron is over here and another is on here, and this is the corresponding spin value for the first copper, and this is the corresponding spin value for the second copper. And if we consider that both the 2 electrons are occupying that one particular magnetic orbital, that means the capital S value, the total spin value is equal to 0, or it is in this particular level where the total spin value is 1. So, when these 2 are in opposite direction and they are interacting in opposite way, we are basically giving a corresponding diamagnetic situation. So, depending upon these copper acetate molecules, whether these molecules are populating the ground level, that the ground state energy level, the lower energy level mostly, and if there is 100% occupancy of this particular level, we get a complete diamagnetic situation. Though the individual centers are paramagnetic, as we theoretically assume that one unpaired electron is present on this first copper center and the second one is on second copper, but if they are not interacting to each other, we get a paramagnetic situation. But when they are strongly interacting, and depending upon that interaction, we can have a ground state level where this S is equal to 0, and we basically get the corresponding energy separation between these 2 levels, which we also can consider as the multiplet width, and this basically is related to the corresponding J value, which is the corresponding interaction constant, not the J quantum number, but is the corresponding interaction parameter what can be detected with respect to that of the separation. So, we get some value which is close to some time to close to this separation, and when this particular level is occupied, we get antiferromagnetic interaction, and when the upper level we get a corresponding ferromagnetic interactions. So, in case of antiferromagnetic interaction, and this particular temperature is very important, and we consider it as the nil point or nil temperature, because this particular temperature is defined in such a fashion that above this temperature, so we have a critical temperature, and above this critical temperature the system is more or less behaving like the simple paramagnetic system. So, if we are measuring the magnetic moment of two systems, where one is a typically paramagnetic system and another is antiferromagnetically interacting system. So, at some high temperature in this region or in this particular region, we are not able to identify the nature of these corresponding species, whether the compound is paramagnetic or antiferromagnetic, that we are unable to identify if we go for the corresponding magnetic measurements in this particular region or in this particular region. So, for that purpose we have to cool down the system and we have to go below this temperature, that means below this nil temperature. What we see that our magnetic moment or magnetic susceptibility is decreasing with the decrease in temperature, which is in opposite form. The behavior what we are seeing over here is the susceptibility is decreasing with increase in temperature, but below the nil temperature the susceptibility is also decreasing with decrease in temperature. And by looking at the shape of this curve, because we can plot in some time also the product of chi-m T versus T also, because this particular thing can justify our concept that at this temperature we have a sudden change in the corresponding alignment of these unpaired spins and the system is behaving as an antiferromagnetic species and we have a corresponding nil temperature. So, this abrupt lowering in magnetic moment with respect to lowering in temperature is basically a clear indication for the antiferromagnetic nature of these species or these compounds. Similarly, another temperature is also can be observed for some other system which is ferromagnetic in nature, where we get a Curie temperature, and above this Curie temperature we see that the system is simply behaving like a paramagnetic system, because at this particular temperature the measurement will not tell you whether our species is a ferromagnetic one or a paramagnetic one. But below this Curie temperature, what we see that below this temperature the paramagnetic system is changing in this particular way, that means it is monotonous and it is also continuous, but for ferromagnetic system there is a abrupt change and it is basically a continuously not a parabolic one, but it is a continuous straight line curve for this and it is increasing in a steep fashion. So, steeply the rising in susceptibility value as we decrease the temperature is a characteristic feature for the all ferromagnetic materials. So, magnetic ordering or magnetic interactions are only observable at some lower temperature. That is why we are all interested to go for the magnetic measurements at lower temperatures. So, that is why we go down to liquid nitrogen temperature, or in some other cases we can go to liquid helium temperature for these measurements. So, what we see that for all these systems, and if we just elaborate it to up to copper, for a D9 system to D1 system, for the entire range from trivalent titanium to bivalent copper, we now know that we have the typical occupancy of these electrons. So, after D5 what we have seen for manganese 2 plus or Fe3 plus, the number of unpaired electron is decreasing as we go for the corresponding pairing in the system for the T2G level. So, in the octahedral geometry, this is for only one particular geometry, because this can also we can calculate it out for other typical geometries of different symmetry such as square planar, square pyramidal, trigonal bipyramidal, etc. So, depending upon these number of unpaired electrons present in all these systems, we have the spin only values in mu b or Bohr magneton, and we can compare these values with that of the observed values which we can determine experimentally. So, experimentally determined quantities are sometimes very much different. What we see from this particular plot, this particular table, that when we see that in case of Mn2 plus or Fe3 plus, the experimental magnetic moment is slightly higher than the theoretically predicted magnetic moment value based on the mu s equation. Mu s equation is that S is a good quantum number. We are not bothering with that of the other two quantum numbers, that means the L values or the J values. But when we move to a D7 system or a D8 system, or in some places also the D9 system, we see that the mu spin only values are always less than that of the range what can be predicted for the experimentally determined magnitude of these values for the different metal complexes. So, for different metal complexes, for simple mononuclear one, we find that cobalt mononuclear compound can register a magnetic moment value of say 5.2, but the spin value is predicting us for 3 electron is equal to 3.87, where n value is equal to 2. So, the magnitude what we can calculate is root over 3 into 3 plus 2. So, is basically 15, root 15 is equal to 3.87, but it is going up to 5.2. So, there is some other thing which is contributing or which is increasing the magnetic moment values from 3.87 to 5.2. Similarly, for nickel 2 plus, it is happening that the spin only value is 2.83 and we are going up to 3.9. So, there is some other contribution which is adding to the corresponding spin only values. Similarly, for copper 2 plus, though the magnitude is less, but it can go from 1.73 to 2.1. So, next what we can do therefore, that we now take into consideration of the L values. So, what are the L values for the corresponding ground state spectroscopic symbol, what we have calculated in our previous class up to chromium 3 plus, that means the D3 system. So, today we will just find out what are the corresponding values for D4 to D9 system, and depending upon the spectroscopic term symbol, we have the S value and the L value and the corresponding J values. And then we can calculate out the corresponding mu J values and mu L plus S. So, those basically can tell us that this mu S is not operating for explaining the corresponding mu experimental values or mu observed values, but mu L plus L can identify the corresponding increase in the magnetic moment values beyond the spin only values. So, that we can see for the different values for say chromium 2 plus. So, if the metal ion is chromium 2 plus, which is our ion, and the corresponding ground state quantum numbers, that means the S values and the L values we can have. Then we can have the symbol, the spectroscopic symbol, and then we can calculate the corresponding mu J value, mu S values what we have seen in the table right now, then mu L plus S values and the mu observed or mu X values, the experimental values for these systems. So, when we have chromium 2 plus, which is a 3D4 system, so is a 3D4 ion, and the corresponding ground state quantum number for capital S is 2, with respect to the 4 unpaired electron, and L value is equal to 2 for the electrons in the d level, and the corresponding spectroscopic symbol which we can find out from here is 5d0, and we are considering this J value as equal to corresponding L minus S values, not L plus S. So, mu J will therefore be 0 since this particular value of J is equal to 0, but mu S is equal to 4.9, which is related to the number of unpaired electron equal to 4, and this 4 number of unpaired electrons, that means the n value equal to 2, that means it has the corresponding magnitude of root over 4 into 4 plus 2, that means root 24. So, root 24 is 4.9. Now, we see that what is the corresponding value for the experimental one, what we have seen just now, that it can range from 5.9 to 5.3. So, what would be the mu L plus S? So, considering both L value and S value, this can be 5.48, which basically justifying the upper limit for the magnetic moment what we can get as an experimental magnetic moment. So, if there is sufficient amount of orbital contribution, our mu S equation is not sufficient to explain the correspondingly observed magnetic moment value, but mu L plus S can be used to determine the corresponding magnetic moment what we experimentally determine for this metal ion system. Similarly, the next one, which is manganese 2 plus, which is a D5 system, and we have 5 unpaired electrons. So, S value is 5 half and L value is equal to 0. So, the ground state term is 6s 5 by 2, and mu spin only value is for 5 unpaired electron, and the observed values are close to 5.9, and this is also very much useful depending upon the corresponding spectroscopic term. This is S, not D, this is S. So, corresponding to the spectroscopic term which is AS, that means we do not have, when we have the S ground state term, we do not have the corresponding orbital contribution. So, for mu J it is also 5.92, this is also 5.92. So, this is for D5 system. Then iron 2 plus, which is the D6 system, S value equal to 2 and L value equal to 2, then the term is 5D4 and mu J is 6.7, this is 4.9 and this is 5.48, and this value is ranging from 5.1 to 5.4. So, again it is close to the corresponding mu L plus S value, like in the case of chromium 2 plus, which is closely related. Then we have the cobalt 2 plus, which is D7 system, S value 3 by 2, L value 3, which is 4F9 by 2 is the term symbol, and the mu spin only is 3.87 for 3 unpaired electron, but the experimental magnitude is ranging from 5.1 to 5.2. So, if we calculate the mu J equation, it will be 6.64, which is quite high compared to the experimentally determined value, but the mu L plus S is quite close to that value, which is 5.20. So, we see that more and more we are deviating from the mu S equation, and we are slowly getting some equation where the mu L plus S values are matching with that of the experimentally determined quantities. So, this typical example, because most of the cases we encounter with several cobalt 2 compounds in either tetrahedral or octahedral geometries which are having registering some magnetic moment which is higher than the spin only value. So, we have the typical orbital contributions. So, we have the next one as nickel 2 plus, which is 3D8 system having 2 unpaired electrons in the Eg level, which is T2G6 Eg2 and L value equal to 3. So, the ground term is 3F4 and the spin only value is 2.83 and the range is also from 2.8 to 4.0, and mu J equation is now quite high, because after this half field level, that is after D5, what we are getting, that continuously we are getting a highest level of this corresponding mu J values compared to mu L plus S, because in this particular case these two values are same, but in this case it is higher than the mu L plus S, in this case it is higher than the mu L plus S, and similarly in this particular case also it is higher than the mu L plus S, here it is 4.47. So, again it is justifying the corresponding higher magnitude of the observed magnetic moment value in terms of the corresponding mu L plus S equation. So, for the next one is the copper 2 plus, which is a 3D9 system having 1 unpaired electron, L value equal to 2, and the term value is again returning back to the D term. So, 2D 5 by 2 with 1 unpaired electron, the spin only calculation gives us 1.73 Bohr magneton, but the experimental value is changing from 1.7 to 2.2 and J value is equal to 3.55 and the mu L plus S is quite high compared to the experimentally determined value of 2.2, but still that some contribution we can have which can basically justify the higher level of this corresponding magnetic moment compared to the corresponding value what we can get from the spin only values. So, we have something that means a corresponding thing what we are getting, that if we have a particular system, that means these electrons, say for nickel 2 plus, what we can have, we have the T2G6 and Eg2 electrons. So, what we will be seeing there, that we have several of these levels, the T2G levels we all know, that dxy, dxz and dyz, and these are dx square minus y square and dz square. So, electrons are there and these electrons are basically moving from one level to the other, and if the corresponding movement of the electron from one particular level to the other level is allowed, that means we see that we can find that we can rotate this electron from one particular shape to the other shape, because this particular orbitals, the dxy, this dxz and dyz are interconvertible in terms of the rotation along some specified axis. So, if the electrons are there in these particular levels and we can move those electrons from one level to the other, so we can have the corresponding orbital contribution, and these orbital contributions are due to orbital rotation. Why we are getting these corresponding L values in the magnetic moment compared to the only mu S values? Because of these orbital contribution to the magnetic moment values, and this orbital contribution is due to the corresponding orbital rotation and the transformation. So, we have therefore orbital rotation and transformation. So, what we see that for the occupancy of these different levels, so 3 rules we must follow for these orbital contributions. The first one is that orbital must be degenerate. That means if we have degenerate orbitals like the T2G set or the EG set, and there will be an energy barrier for rotation. So, if they are degenerate, then we can have the movement from one level to the other, otherwise there will be an energy barrier for rotation. So, whether these orbitals are degenerate or not, that will dictate whether it can contribute the corresponding orbital moment to the spin moment. Then orbitals must be of same shape. What we are talking about, these dxy and dxz orbitals, then they must be transformable from one to another by rotation. So, they are transformable from one to another by rotation about a suitable axis. So, we should that also consider, and when this rotation we are allowing, the orbitals which we are talking about for the movement of the electron to the other, so they should not contain any electron. So, these orbitals should not contain electrons of the same spin. So, these are the 3 basic rules what we can follow for this orbital rotation model and the transformation model. So, these how we can apply, we just see that if we have the dz square orbital and we have seen the T2G level of orbitals and the dx square minus y square orbital. So, whenever we have an electron say in this dz square orbital, that means the electronic configuration is dz square 1, then we see that whether this can be transformable from one to other by rotation or not, but this dz square is not transformable into any of these 4 orbitals, into any of the other 4 orbitals, that means dx square minus y square and the T2G set. So, if we have electrons in EG level or E level, so when the electrons are present in EG or the E level, they cannot make any orbital contribution to the spin moment. So, do not contribute to the spin moment. So, we will have some situation where these electrons are there, but they will not definitely contribute to the corresponding spin moment. So, these two, therefore, the dx square minus y square and dz square, which are the EG set or the E set. So, these two we cannot interconvert, and therefore, these two will not contribute any magnetic moment contribution with respect to the mu L values. So, they constitute basically a non-magnetic doublet. So, these two levels we can consider as non-magnetic doublet. So, they are non-magnetic in terms of the corresponding orbital contribution, but if the electrons are there, the spin moments are always available, but the orbital moment we cannot. So, the next one, the T2G set level, that means if we have the dxy. So, this dxy orbital we all know that is this is x and this is y. Shape of this dxy orbital is like this, and if we rotate about y axis, so about y axis we rotate this orbital. So, it can go from this, it is not moving from this x plane. So, it will be going for y and this perpendicular z plane. So, it is basically giving rise to the dyz orbital. So, if we can go for this dxy at the rotation and y axis to dyz. So, electron from this level can go to this level and can contribute in terms of this orbital rotation. So, orbital rotation model predicts us that if we have an electron in the dxy or dxz level, that will basically contribute the magnetic moment in terms of these orbital contributions. So, if we have the d1, d2 in octahedral geometry, then what we do expect that we have the either the dxy1 or dyz1 and dxy1, that means two electrons in these two T2G level in octahedral geometry. So, they basically generate orbital moment. So, would be able to generate orbital moment, but D3 in the same octahedral geometry is violates the rule what we have predicted earlier, the rule 3, that means the orbitals should not contain electrons of the same spin. So, already we have these electrons in this spin. So, this will not contribute that particular rule. So, it will not have in octahedral fields, the D3 will not have this orbital contribution. So, it violates rule 3, but the same situation is completely reversed if we go for the other geometry. The most common geometry what we are talking all the time is the tetrahedral geometry. With a D3 electronic configuration, we have E2 and T21 electron configuration. Since like this D1 system, we now have T21 system. So, it will have then the corresponding orbital contribution. So, this electronic configuration for D3, which is not giving any orbital contribution in octahedral geometry, but can give rise to the corresponding orbital contribution in tetrahedral geometry. So, it therefore gives orbital contribution. So, we find these are very important and very interesting thing in terms of these corresponding orbital contributions. So, we have in terms of the corresponding term symbols that if we have the high spin system for D1, D2, two unpaired electrons in the T2G level. Similarly, the situation is same when we cross the half filled configuration, that means after D5 we have D6 and D7. So, likewise what we see for this D1 and D2 case in octahedral geometry, similarly the D6 and D7 also can have in octahedral geometry this orbital contribution. So, can have orbital magnetic moment, can have orbital moment. So, in terms of these corresponding term symbols, what we see that in case of nickel 2, which is 3d8 in octahedral geometry, we have T2G6 and EG2 configuration, and the corresponding ground state term after crystal field splitting of the 3F term is 2Ag, and this 3Ag term is due to the corresponding configuration of T2G6 Eg2, and this can go for the other two configurations like the excited levels, which are T2G5 Eg3 for the excited level term, which is 3 T2G2, and T2G4 Eg4, which is for 3 T1G term. So, these are the two excited levels. Since the ground level is A term, that means when we have the electron field in the Eg level, and Eg level is the non-magnetic doublet level. So, we do not have any contribution, any orbital contribution from the ground state electron configuration, but from the table what we have seen that in case of nickel 2 plus, we have the magnetic moment which is in excess of the spin only value, which is 2.84, but experimentally the amount of magnetic moment what we get by determining the magnetic moment experimentally is sometime close to 3.2 or 3.3. That means there is definitely the corresponding orbital contribution, but that orbital contribution is not coming from the corresponding ground state term, but it is coming from the excited state terms, and these excited state terms we have these unpaired electrons basically in the Eg level as well as in the T2G level, because the T2G level is not filled as T2G6, but is T2G5, which is similar to T2G1. That means like this system or this system. So, they have orbital contribution or orbital moment. So, these two configurations, the 3 T2G and 3 T1G configurations, these are the two excited states, and these excited state these two excited states can produce orbital moment. That means these two levels will contribute the magnetic moment for this nickel 2 system, where we have magnetic moment higher than the spin only value. So, if we just consider these two levels, and we all know that these are basically related to the crystal field splitting parameter, the 10 dq values. If it is in octahedral geometry, it is 10 dq O value. So, if we have a small value of this 10 dQO, we basically get for that this excited level, that means 3T2G, the first one, this one 3T2G level would be closer to 3A2G level, that means the ground state level. So, what happens therefore? Therefore, we can have this corresponding spin orbit coupling. So, this particular thing, the mixing of the excited state, we call it as a spin orbit coupling, and which is mixing the two states, that means 3T2G is mixed up with 3A2G, and as a result we have above the spin only value we have the corresponding magnetic moment. So, similar thing also happens when we get the corresponding cobalt system, which is 3D7, and in case of this, the cobalt, we all know that cobalt is very useful in giving the corresponding compounds in the tetrahedral geometry, such as cobalt NCS whole 4 2 minus. So, in this particular compound in tetrahedral geometry, we have the corresponding electron configuration is E4 T2 3. So, we have in this particular situation the ground state is 4A2, which is also not contributing any orbital moment to the system, but this particular 4A2 term will have a 4T2 term related to movement of the electron from one particular electron from here to here. So, this particular one will be E4 T2 4. So, for an electron configuration of E4 T2 4, we have an excited state, which is the first excited state, and these two levels, that means the first excited state and the ground level, they are again separated by the corresponding crystal field term, that means which is 10 dQt. So, if they are separated by 10 dQt, and again due to the mixing, what we get that the corresponding magnetic moment, what we are getting, and we are justifying this magnetic moment in terms of the corresponding L plus S values, is that mu spin only values multiplied by 1 minus alpha into lambda divided by 10 dq. It can be the corresponding dqo, that means dq octahedral, or dqt for the tetrahedral geometry. And in this particular equation, where alpha is a constant and it has different magnitudes for different terms, will be equal to 2 for an E ground term, and it can be equal to 4 for an A term or A2 term like this. So, these are therefore, so this A term and E term will not contribute any magnetic moment in terms of this orbital contribution to the spin only value, but T term can contribute, but these T terms are arising as the corresponding excited state values, and therefore, we can find out from here the corresponding lambda value, which is nothing but the spin only coupling constant. So, the coupling, the mixing of all these things will therefore tell us that these terms, the A and E terms, will not give any magnetic moment in terms of these corresponding orbital moment values. So, for these two, the orbital moment values are not available, but for T term has the corresponding orbital moment. So, whenever we have the corresponding T term, we get any orbital contribution from this particular system. So, this particular thing will tell us that why we are getting some amount of magnetic moment which is in excess of the spin only values. Thank you very much.